Hello students, this is Mrs. Buelson. We're going to work together today on the beginning of the constant acceleration practice number 2. The packet of worksheets that you've either already picked up, let's see, I'm just counting pages, we've got 3 pages of worksheets. You've either already picked it up or it's available to you today. So we're going to work together for the first page, and then we're going to do a couple of example problems throughout the packet, and then you're going to spend the rest of the day working on this on your own. And this is due at the start of class when I see you again. For the red day, that's going to be Thursday, and for the black day, that's Friday, due date at the start of class. So, name on it, period, in case you lose it. So we start with thinking about free fall speed, and then we're going to think about free fall distance. So the equation for free fall speed from our lecture is V2 equals V1 plus acceleration times time. And in free fall, that acceleration is 9.8 meters per second squared. On this worksheet, we're going to actually round up from 9.8 to 10. It'll just make our calculations a little bit simpler. So V2 is the speed you end at, your speed sometime in the future. V1 is your starting speed, acceleration for A, and time for T. And again, in free fall, we know the acceleration, 9.8 meters per second squared, or we're going to go ahead, like I said, and round up to 10. So our first question is not about free fall speed at all, but it's how we think about free fall. So Aunt Minnie gives you $10 per second for 4 seconds. How much money do you have after 4 seconds? So the process of using this equation is what you do when you think about getting $10, then getting another $10, then getting another $10, and then getting another $10. 4 seconds. Second 1, 2, 3, 4 gives you a total accrued money of $40. We could think about it in terms of the equation. Speed 2 is speed 1. You started with $0, so 0, plus how much you sped up, 10 meters per second every second, or $10 per second every second, times how much time you've been speeding up for. What we did here, adding 10 plus 10 plus 10 plus 10 4 times, is the same as what we're doing when we use this equation. Our answer is $40. So now we convert our thinking from dollars to velocity. A ball dropped from rest picks up speed at 10 meters per second every second. After it falls for 4 seconds, how fast is it going? So our answer again is 40 for the same reasoning. And then again, we use this keyword here from rest. That means V1 is 0. Okay, so now we think about what if you didn't start from rest? What if that starting speed or that starting money was not 0? So you start out with $20 and Uncle Harry gives you $10 each second for 3 seconds. How much money do you have after 3 seconds? So now we think not 10 plus 10 plus 10 plus 10. Now we think you started with 20, and then for 3 seconds you had 10, 10, and 10 again. So we're thinking, what happens if your starting speed is not 0 but something else? So 20, 30, 40, 50. You have $50 after 3 seconds. And then similarly, if you throw a ball with an initial speed, that V1 is no longer 0. So we can think 20, starting speed of 20, plus 10 plus 10 plus 10, or we can think in terms of our equation, V2 is V1 plus acceleration times time, so V1 is 20 plus acceleration of 10 times 3. Same math, just kind of thinking about it slightly differently, either thinking about it in terms of what you do each second, or thinking about it in terms of what you do each second using the equation. Same answer, 50 meters per second. So now what if you throw something into the air up rather than down? So here we had thrown it down and it sped up as it went. So we had a plus. What if you throw it up into the air? So if you throw something up into the air, it slows down. As you know, you've lived on the earth long enough to know that. So the way we think about that is like you have money and you give it away. So you have 50 and you pay Aunt Minnie $10 per second. Now we're thinking not 50, 60, 70, 80. Now we're thinking 50 every second you take away 10. So 50 minus 10, minus 10, minus 10. How many times do you subtract 10 from your 50 to get to 0? When does your money run out? So 10, 20, 30, 40, 50, we've subtracted 5 times. We have 5 seconds until we run out of money. Same idea, but for something straight up into the air. So we start with a speed of 50. We're thinking on the way up you slow down. So V2 equals V1 minus acceleration times time, because you're losing speed rather than gaining speed. So V2, when you run out of speed, 0, is equal to V1, 50, minus 10t. And so we're saying how many times do I multiply 10 to get to 50 so that I subtract 50 from 50? And our answer, the same, 5 seconds. Let me try to show you that algebra a little clearer. There's not a lot of workroom on this worksheet. Over here, you say 50 minus 10t is 0. The formal algebra is to subtract 50 from both sides. So minus 50 equals minus 10t. And then we need to isolate that time, so we divide both sides by 10. And really we should divide both sides by negative 10. But since there's a negative on both sides, we can also kind of ignore it. So 10 over 10, done. T is equal to 50 over 10, or T equals 5. So that's the formal algebra. But what we're doing is exactly what we did here with $50, subtracting, subtracting, subtracting until we get to 0. So what will be the arrow's speed 5 seconds after you shoot it? Well, by gosh, we just said 5 seconds. The whole point is that's when you run out of speed. What will its speed be 6 seconds after you shoot it and 7 seconds after you shoot it? So now we have to think about the physics involved here. Something going up loses 10 meters per second every second. It gets slower and slower and slower. At the top, it pauses, and then it does exactly what it just did, but in reverse. It gets faster and faster and faster. So if it takes 5 seconds to get to the top, and at 5 seconds it's at 0, now it's like it's been dropped. So 6 seconds in, you're now at 10 meters per second. You've gained 10 meters per second. At 7 seconds, you're 2 seconds into the fall. You're going 20 meters per second. So we can track the speed of an arrow thrown up, or shot up into the air, second by second, by thinking about how what happens on the way up is the same, but in reverse, as what happens on the way back down. So now we're going to think about that in more detail. So you can do this on the very last side. I just brought out a clean sheet of paper. On the very last page of your packet, it's a blank sheet. I want to think about that idea of moment to moment. What is that arrow doing? So here's our starting, there's our starting line. And we started out at 50 meters per second. 50. So I'm going to have to space them out a little bit, right? So 1 second later, it's not going so fast. So 40. So this is V, 50. V, 40. Then 30. Then 20. And they're getting closer together as they go slower, right? The dots don't cover as much ground. The arrows don't cover as much ground. These are kind of a motion diagram. So 30, 20, then 10. Oops, I made it a little too close. And then at the peak, you're not going at all. Right? So we're saying we're losing 10 meters per second of speed, 50, 40, 30, 20, 10, 0 on the way up. And then on the way back down, at the same place, at equal amounts of time away from 0, away from the top, I'm going the same speed. So So this is 1 second before the top, I'm going 10 meters per second up. This is 1 second after the top, I'm going 10 meters per second down. So here I am 2 seconds from the top, I'm going 20. Here I am 3 seconds from the top, I'm going 30. And I'm trying to draw my arrows to be about the same length, right? They're pointing in opposite directions, but the arrows are the same length, indicating the speed is the same, even though the direction is different. So 40. And then finally when I get to the bottom again, or wherever this is my launch place, right? This is like where I'm holding the bow. This is 50, back down towards the ground. So we have this idea that the motion is symmetric. When I say symmetric, this is what I mean. So here's like our top point, and everything that happens on the way up happens in reverse on the way back down. So now we might want to know not how fast it's going, but where it is. So how far is it to the top? How far is it at each second? So our equation of how far you go is starting speed starting speed times time plus half times acceleration times time squared. That doesn't really work so well unless we kind of get fancy with our math. It's easier to think of it for dropped things. But the second half of this arrow's flight is like I climbed up on a ladder to the top and dropped it. So I could figure out from the top to ground. I'm having a tough time with spelling here. From the top to the ground, I know that it takes a time of 5 seconds. And so I can figure out how far it falls from the top to the ground using my distance, right? So distance fallen is, I started at the top, v1 at the top, times time, plus half times g, right? Half times acceleration due to gravity, which we're rounding up to 10, times how much time it spends falling from the top. So that was 5 seconds. This v1 at the top is 0. v1 at the top is 0, so I can eliminate that. That's where my problem happens. So now again, I'm finding how far does it fall in 5 seconds of falling from the top. Half times 10 is 5, times 5 squared is 25. 5 times 25 is 125 meters. So now I know how high it is. This zigzaggedy red line, I know, is a total of 125. I could maybe do that like this. 125 meters is how far it goes. Now I might like to know where is it every second. So again, I'm going to figure out how far it falls in 1 second, how far it falls in 2 seconds, how far it falls in 3 seconds, how far it falls in 4 seconds, and then I can know where it is throughout its trajectory. So I'm using the same equation. I'm using this idea that from the top, again, each second. So where it is starting speed times time plus half times 10, we're rounding up, times time squared. And I can simplify. From the top, it's always 0. And half times 10 is always going to be 5. So from the top, where it is 5t squared. This should be familiar to you because we did this for that pumpkin graphing exercise. So 5t squared. So 1 second down, this distance, 1 second from the top is 5 times 1 squared. 2 seconds from the top, not sure how to quite draw that accurately, is 5 times 2 squared. 3 seconds from the top is 5 times 3 squared. 4 seconds from the top, this is getting a bit redundant, right? Is 5 times 4 squared. And so we can now know where it is every second, and we know how fast it's going every second. 5 times 1 squared is 5, 5 times 2 squared, so 5 times 4 is 20, 5 times 3 squared is 5 times 9, which is 45, I think, and 5 times 4 squared, 5 times 15, no, excuse me, 5 times 16, that one, I think is, nope, I'm not sure, is it 80? Yes, 5 times 4 squared is 80, okay, and so we know it's ground to the top is 125, so from the top 1 second down is 125 minus 5, that's 120. From the top 2 seconds down, 125 minus 20, and so on. Okay, so that lets us answer our free fall distance. We've had to think about the arrow second by second by second. So speed is one thing, distance is another. Where is the arrow you shot up at 50 meters per second when it runs out of speed? We've just discovered that it goes 125 meters to the top. How high will the arrow be 7 seconds after being shot up at 50? So we come back to our map here. So here's 5 seconds, 6 seconds, 7 seconds. So 7 seconds, it's fallen 520 from the top. So 125 minus 20, 105 from the ground. Aunt Minnie drops a penny into a wishing well and it falls for 3 seconds before hitting the water. How fast when it hits? So she drops 3 seconds. We're saying speed is 3 times 10 plus 0, right? So 30. That's back to thinking the way we were above here in the free fall speed. What's the penny's average speed during this 3 second drop? Well, it started at 0, it ended at 30, and so average is value 1 plus value 2 divided by 2, so 15. And so how far down is the water surface? One way to think about it is our equation, distance is half acceleration times time squared, or we could also think about it in terms of average speed times time. We'll get the same answer. So over here, we said something falling for 3 seconds falls 5, 20, 45 using the equation how far is half times 10 times time squared. We can also think about it in terms of average speed times time if we like. If that's easier for you, average speed for those 3 seconds is 15 for 3 seconds, and voila, we get 45, the same answer. If this worked for you, this is fine. It's an extra step. You have to find the average speed during that time, and then you multiply average speed times time. You can also do distance fallen is half AT squared. Okay, Minnie didn't get her wish, so she goes to a deeper wishing well and throws a penny straight down at 10 meters per second. How far will this penny go in 3 seconds? You can find average speed. So she started at 10 meters per second. In 3 seconds, she goes 10, 10 more, 10 more, 10 more. So she's going 40 meters per second. We can divide by 2 for average. So that gives me an average speed of 25 meters per second for 3 seconds. Average speed 25 times 3 is 75. Or I can use how far I fall is speed times time plus how much farther I went because I accelerated, and that is 10 for 3 seconds plus half times 10 times 3 squared. So 10 times 3 is 30. 5 times 3 squared, ooh, dang it, I need a calculator. I think that's 45, right? 5 times 3 times 3 is 45. 45. So 45, 55, 65, 75. We get the same answer either way.
No substitute?
No, the substitute's coming. Sorry, guys. I'm not sure how to pause the recording. So I have a child care emergency today, and that's why you have a substitute. Just had to check. Okay, so now we're going to talk about acceleration and free fall, and we're thinking about how far something falls and how fast it's going as it falls. The equations are how fast, how far. We've written it as V2. V1 is 0 if you've dropped it, so 10 times time, or how far, half times 10 times time squared. Those are our versions of the same equation. So the speedometer, so this is supposed to be the speedometer in a car, and the odometer, that's how far you go, how fast you go. The speedometer reading increases by the same amount. It increases by 10 meters per second every second. The increase in speed is called acceleration. That's what it means. So the distance fallen increases as the square of what? So what item is squared in these equations? Time. If you take 7 seconds to reach the ground, then the speed at impact is, so we're thinking 10 times 7 seconds, 70 meters per second. The distance fallen is half times 10 times 7 squared. So 5 times 49. 5 times 49 is 245. Ooh, I hope that's right. I think that's right. 7 times 7 times 5. Yes. Okay, and its acceleration is, that's how we knew, right? This acceleration in free fall is 10. So now I want you to fill out speedometer, odometer for falling for 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. And by gosh, this is short like what you did for the pumpkin, not surprisingly. So you'll do this on your own. Now let's look at some of the problems. So now I'm on page 3. So for a long time, it was the dream of many runners to break the 4-minute mile. Quite a few runners have done that by now. So we have Steve Graham running a mile in 3.81 minutes. What was his average speed in miles per minute and miles per hour? So we're saying speed here, we're going way back to the beginning. Speed is distance divided by time. Well, he does 1 mile in 3.81 minutes. 1 divided by 3.81. Not so hard. We do need a calculator for this. So 0.262, let's say, miles per minute. And then it says, please change that to miles per hour. So I have A of 0.262 miles per minute. Now I'm going to change it to miles per hour. So I'm thinking 0.262 miles minute times, how do I get it to hours? Well, there are 60 minutes in 1 hour, and I want hours to be in the denominator. So I'm going miles, not multiplied by anything, minutes and minutes on top of each other, so they cancel out, and I'm left with hours. So 0.262 times 60 is, right, 0.262, 60 divided by 1 is 15.7 miles per hour. That seems kind of small. 15.7 miles per hour. I guess, no, I don't know, 4-minute mile? Sure, why not? Okay, so this is another question about sort of constant speed but in pieces. You're going to draw a graph of the motion. You're going to find out if she makes it to class on time. You might try to draw the graph first. Draw the graph first. If you need another piece of graph paper, you know where to find it. Let's look for a acceleration question. Here on page 4, while driving his sports car at 20 meters per second down a 4-lane highway, Eddie comes up behind a slow-moving dump truck and decides to pass it. If Eddie can accelerate at 5 meters per second squared, how long will it take him to reach 30 meters per second? So this is a acceleration, because I know the acceleration, so constant acceleration. I have a starting speed, right? This is his while driving sports car, V1. So I might like to draw a diagram of this. Sports car, V1 is 20, V2 is 30, and as this happens, acceleration is 5. And I want to know, how much time did that take? Well, if I've got V1 and V2 in acceleration, the first equation, V2 equals V1 plus AT, would seem to be the right choice. So V2, 30, equals V1, 20, plus acceleration times time. So I need to subtract 20 from both sides. 30 minus 20 is 10, equals 5t, and then I divide both sides by 5. T equals 2. 2 seconds. All right. You have the rest of the period to work on these problems. This is due at the start of class when I see you again. For a red day, that is Thursday. For a black day, that is Friday. And I'm saying it's due at the start of class. I will take any questions you have at the start of class on those days in case you get stuck on some of this. But what you don't finish in class today is homework. You need to have tried every problem before I see you again at the start of class. Days already stated. See you guys later.